I think I'll bring it over here. Are you... yeah, okay. I'll just use this one. Yeah, that's fine. Have you got my slides? Okay. All right. I'm going to talk about some speculative theories about the very early universe. And funnily enough, it does it does connect with previous speakers. The speaker just before me has said everything that comes from physics is true. So clearly everything I'm going to say is true. But I don't want you to believe that. People have perhaps too much respect for physics, and especially when we deal with the most difficult questions of all, like what happened at the Big Bang. I really don't have any better idea than you do, okay? All we can do, which perhaps some of you can't do, is make consistent mathematical models of the Big Bang and then do our best to prove them wrong. Okay, so the whole attitude which we take is one of skepticism and inquiry. It's a very exciting field because we now have some data which people didn't have before, but I'm not going to give you any answers, and I'm not sure I'm going to give a talk if there's no slides. You just press Control F7.
Yeah, no, it doesn't seem to click on.
Really? Okay, I'll give a talk about the real IQ. Okay, I'm just going to start anyway. Most of my talk I can illustrate with my hands. The topic of my talk is what banged, okay? And that question was put to me by a school teacher who taught me when I was 8. And she's now in her mid-80s, and I went up to Edinburgh to visit her and tried to explain what I work on to her. She very quickly, her eyes glazed over. She said, look, there's only one question that mattered. And that's, what banged? In a very strong Scottish accent. She said, I've asked this to every single scientist who come to talk about astronomy or cosmology, and nobody has an answer. Well, that's the topic of my talk. It's exactly what we're trying to understand, is what banged. Now, this question has become more and more and more important to fundamental science. Okay? The reason is partly because we now have a rather complete description of the history of the universe, a very successful description. The hot Big Bang theory, invented in the 1920s and 1930s, successfully explains how much of the universe is in hydrogen, helium, lithium, deuterium, the light chemical elements. It explains how the universe emerged at 300,000 years old. It was full of a hot plasma. This plasma radiated the cosmic background radiation to us, which we can now detect. And we can see the early pattern of structure in the universe that later turned into galaxies and stars. So that's one reason why this Big Bang theory is so successful. Are we still struggling? It's on the wrong screen now. Okay. Okay, so here we go. Very good. Okay, next slide. Oh, you want me to do that? Yeah. Okay. No, it's fine. Okay, so here is just a artistic image, which should work, but doesn't. Okay, we'll forget the artistic image. This is the history of the universe. Big Bang, formation of the chemical elements, stars, galaxies, black holes, and we live today 14 billion years after the bang. In 2001, this satellite was launched, called the Wilkinson Microwave Anisotropy Probe, and it sits far out in space and mapped the sky. And this picture shows you how far the subject has come in the last 15 years or so. In 1992, our picture of the universe was revolutionized by the Cosmic Background Explorer satellite, COBE, and which gave us the first picture of the variations in density in the very early universe. And so this is a picture of the universe as it was only 400,000 years after the Big Bang. In 2001, WMAP flew, and this is its picture. Unfortunately, projection isn't brilliant, but it's really a much higher resolution, very beautiful picture of the universe as it was. Now, what I want to emphasize is the only way we understand the universe is by making theoretical models of it. I haven't done an experiment this morning, and there's a deep symbolism in that. We cannot repeat the experiment in cosmology, okay? In the rest of physics, when you're probing some phenomena, you can do experiments, you can manipulate it, you can do things with it. We cannot do that with the universe. Maybe that's a good thing, but we can't do it. And so what we do instead is we make mathematical models through which we interpret the data, and then we check, are those models consistent with new measurements? So cosmology rests on mathematics more than any other area of science. And the basis for cosmology is this guy with the bad hairdo, and here is his equation explaining how the curvature of space-time is related to the energy within space-time. And this equation is the foundation of all cosmology, and I can't really explain it to you, but that's the way it is. Now, this is an amazingly successful theory. Here is the prediction of essentially following from Einstein's theory plus some plasma physics that the fluctuation level, how much the temperature fluctuates in that picture WMAP made against the angle on the sky in degrees, going from 100 degrees down to 1/10 of a degree, the fluctuation level follows this curve. Okay, so the theory is that the thin line, and the data are the points here with error bars. And this is just an astonishing agreement. We do understand the entire visible universe with incredible accuracy, and far better than we understand a snail or even a bacterium. We do, because those are complicated objects. The universe is really an amazingly simple place in which the same laws of physics which apply here in this room apply on a scale of 14 billion light years. Okay, so the universe is comprehensible. This is a prediction I made as a young researcher. Nobody had worked out what the polarization of the sky should be, and we worked this out, and in 2001 it was measured, and it agrees perfectly, and there are no free parameters in that prediction. It's just either right or wrong, and it turns out it's right. Now, this is the conventional model of the universe, which has emerged over the last 25 years. It's called the standard inflationary model. So we live here. Here's our satellite looking back in time, because as the light we receive comes to us from distant regions of the universe, and we see them as they were when they emitted the light, so some time ago. So just by looking out, we're looking backwards in time. And we see galaxies, we see the development of galaxies, we see a period called the Dark Ages, that's before any galaxies formed, and then we see this green oval represented here, which is the sky, the cosmic background radiation, and that covers the whole sky. Now, what happened before that? The universe was full of a hot plasma, and as we trace it back, we get to a point called a singularity. the density of the universe was apparently infinite, and all of the equations of physics fails, and we can predict nothing at all. Now, the conventional theory has been to assume that just after the singularity, for some reason we do not understand, the universe was full of some energy called inflationary energy. Okay, this was postulated in order to explain how the universe became so big and smooth and how it acquired these small fluctuations you see on the sky. So this is inflationary theory. You say, well, we can't understand the Big Bang, so let's just assume that just after the universe sprang into existence, it was full of some energy which blew it up and made the ripples on the sky that we see. That's the standard theory, and I'm going to explain something different. I've always had problems with this theory because it doesn't explain the beginning. And some people have tried to explain the beginning, and so far those descriptions have failed. Now I want to tell you a little more about the universe and its puzzles. One of them, which is shown in this picture, is that the universe seems to have begun to blow up again. So there's a postulated period of blowing up during inflation. It seems to have started blowing up again. That's called dark energy. And here's a picture made by my astronomer colleagues of dark energy. Actually, I confess it wasn't made by them. It was made by me. But it's the best picture we have of the dark energy. It fills all of space. Only gravity feels it. And it is repulsive. It's like this inflationary stuff. And it blows up the universe. So this is something discovered within the last 8 or 10 years, and there are lots of different lines of evidence which agree that space is not empty of energy. The vacuum actually has some energy, and that is causing the universe to blow up. It's like inflationary energy. Now, there's a very big puzzle about this, and when I say a big puzzle, it's a Google puzzle, which is that the model, the standard model of cosmology, has to be adjusted so that the inflationary energy is 10 to the power 100, that's 1 with 100 zeros after it, times bigger than the dark energy. Okay? And this fact has driven some people to despair. Okay? So basically you have to have 10 to the 100 times the repulsion to blow the universe up at the beginning that we actually observe here. So when you try to make a complete model of the history of the universe, you have this number, 10 to the 100, and nobody can explain where it comes from. Some people, in their desperation, have said, well, the explanation is we live in a multiverse. There are many different universes. We're only in one of them, and there are at least 10 to the 100 different universes with different dark energy. The universe we're in was selected by our existence. Okay? This is called the anthropic principle. It's a sort of a way of dealing with an inconvenient fact that the universe seems very ugly, that you postulate many, many other universes, and you say we couldn't have lived in the other ones, so we'll ignore them. And so this has become quite popular. Now, in my last few remaining minutes, I'm going to explain how we've tried to make an alternative to this picture, in which we actually explain the Big Bang as a physical event occurring in a pre-existing universe. I'm going to have to go quickly, but our theory is based on something called M-theory, which is a unified theory of all the particles and forces in nature. And basically, it's along the line of Einstein's thought, but it includes particles, strings, membranes, brane worlds, objects of different dimensions, which all interact with each other. In this theory, there are not just 3 dimensions of space, there are 10 dimensions of space in all, and there are 7 additional ones to the ones we see. 6 of them are curled up in a little ball at every point of the world we live in, and their size and shape determine the elementary particles and what are called the constants of nature. Now, one point I want to emphasize, so this is the best theory we have of all the laws of physics put together. One thing I want to emphasize is that the physical laws we see, electromagnetism, strong and the weak force, they are determined by the configuration of these extra dimensions. And like everything else, they came out of the Big Bang. Okay? So if you want to understand why are the laws of physics the way they are, within this theoretical framework, you have no choice but to understand the Big Bang. And so that's yet another reason why we have to understand the Big Bang. The seventh dimension in this theory is a bit like a sandwich, okay? That there are two sheets, which are the three-dimensional sheets or the three-dimensional world we live in, separated by a small gap. And this model can explain ordinary matter and also dark matter. And I just want to show you a little movie of our mathematical theory, which of course won't work, because this is on an Apple. Sorry, it'll only work on a Windows machine. Hopefully they'll put a link to a website where you can see this movie. Okay, in this model, so basically this model consists, I'm going to have to explain this with my hands. There are two parallel sheets, each one is three-dimensional, and this model was not invented to explain the Big Bang, it was invented to explain all the forces and particles of nature. What we realized is that within this model, you see the separation between these sheets is very, very tiny, far smaller than an atomic nucleus. There's a very, very tiny gap. But within this model, there's no reason why these sheets cannot move and collide. And so we tried to make a mathematical model of the Big Bang as simply a collision between these sheets. When the two sheets collide, there's a release of energy and radiation, just like a bang. You needed the Big Bang. And furthermore, as these two sheets approach to collide, they can develop the ripples which would later generate the density variations that we see in the WMAP picture. So I'm sorry I can't show you the movie. In this new model, inflation isn't needed. There isn't a period of exponential blow-up of the universe just after the singularity. In fact, there isn't a singularity. The Big Bang is a normal physical event occurring in a pre-existing universe. And it turns out that in this model, you don't need inflationary energy. The dark energy, which we've now observed, drives everything. It causes the universe to blow up, and its decay is what leads these two objects to collide and create the next Big Bang. So this is a theory, as is a cyclic theory of the universe. I can't show you all the details of it. Both models agree with the current data. How do we decide which one of them is right? And as I said, we have no particular prejudice about this. Obviously, we'd like our theory to be right, but we don't know that. So we have to do more observations, and we have to try to find mathematical flaws in either model, or inconsistencies. Now, amazingly enough, there is an observational way to tell what happened at the Big Bang. There is nothing in principle preventing us from measuring what happened at the Big Bang. And the way we do it is using gravitational waves. We know these exist, but they have not been directly detected by laboratory experiments. Now, next year, this satellite will fly. It's like WMAP, only better. And the European Space Agency will launch it. It will make a picture of the sky. And from this picture, you can measure the gravitational waves that came out of the Big Bang. Inflation, the theory that there was an exponential blow-up of the early universe, predicts one pattern of gravitational waves. The cyclic model, where there are collisions between these extended objects, predicts another pattern. And they can actually be distinguished, so Stephen Hawking has bet me that this satellite will disprove our theory. Okay? and it'll fly next year. We haven't agreed on the terms of the bet yet. I said I would take any amount of money at even odds, but he declined that. I think he doesn't want to bankrupt me, so we'll have to invent something else. I also said I could go into space instead of him, because he's planning to go into space, but he didn't want to give me that. Okay. Another experiment which will go up is a laser interferometer in space called LISA. Will fly in 2013, and that will look for the gravitational waves coming out of the Big Bang, and different theories make different predictions. What I find so fascinating about this dichotomy we now have between the Big Bang as a sort of inexplicable, mysterious event where you have to throw in some inflationary energy, that's the one theory. The other theory is no, it's a rather gentle physical process. It's one of many bangs. There will be bangs in the future. There were bangs in the past. The basic question is whether time began or didn't. And as far as I can see, there are only two options. Both ideas can actually be tested through theory and observation, and I would advise you to place your bets now. Okay, thanks.